Greetings, everybody. Learning is a hobby here. I want to continue with the little side project that I have going on with Terry Tao's Analysis One book. I already posted the video for section 2 point the section summaries for section 2.1 and 2.2. There was a slight mistake that I had in section 2.2, so I want to start by just fixing that. It is fixed. Just so you know, I did post the fix of the mistake in the description bar, like I usually do when I notice that there's a mistake of the video for 2.2, so you can look at that. But I'm going to start this video with fixing it anyway. And then in this video, the rest of it will be just doing the exercise set for section 2.2. I am almost done with writing up the notes for section 2.3. When I finish that, I'll write up, when I finish writing up the summary, then I'll make the video on that. And then there's one exercise set for section 2.3, and then we'll be on to chapter 3. And also just a reminder, I will be posting the appendix A on from this book on the Patreon page. Appendix A is on proof techniques and some stuff with logic and sets and so on. So requisite material that you need to know in order to do proofs and that sort of thing. So I'll be posting the appendix stuff on, I'll go through the appendix and post everything about that on the Patreon page. So let me bring up my notes for section 2.2, and I'll just fix that one problem, and then we'll look at the exercise set. Okay, so the problem was in the note that he had or I think he calls it a remark. There's like a remark after the definition of addition in section 2.2, and then right after that he has this like little statement that he has using axioms 2.1, 2.2, and 2.5. We can show that the sum of two natural numbers is again a natural number, and he asks why. He doesn't state it as a theorem or anything, or he doesn't say prove it in any of the exercises. He just asks why. And whenever you come across something like that in a math textbook, you want to try it, because that's why the author wrote the question why there. So I have my proof here fixed. I don't know what happened when I in the previous set of lecture notes that I had. What I usually end up doing is writing everything out on a piece of paper first, and then I transfer it over to the Jamboard on Google, and I must have been distracted or something. I don't know what happened, but watching the video back after I posted it, I realized that this was not correct. So I just wanted to correct that for you guys. So here's the proof of that statement. Again, the statement is the sum of two natural numbers is again a natural number, and unsurprisingly, it's done by induction. So let n be a natural number. Then here's the base step: 0 plus n is equal to n, which is obviously a natural number, so that checks out. Then going on to the inductive step, assume n is a natural number such that m plus n is a natural number for all m and n. Then the successor of n is a natural number by axiom 2.2, and the successor of n plus m is a natural number by axiom 2.2. Therefore, the successor of n plus m is equal to the successor of n plus m. That's just by the definition of addition, is equal to n plus the successor of m, which those two things are equal by one of the previous propositions that we had. And that's obviously a natural number because it's equal to n plus the successor of n plus m, which we know already is a natural number. So that shows that the sum of any two natural numbers is a natural number. So I just wanted to fix that in the video, in case people didn't see that it was corrected in the description bar. But anyway, let's go on now to the exercise sets for section 2.2, which is not a very long exercise set. I think there's like 6 or 7 problems, I forget now, but and they're all relatively short, with the exception of like one of them. But we'll go through my solutions here. So let's start with the first question, exercise 2.2.1, prove proposition 2.2.5. And he gives a hint here. He says fix 2 of the variables and induct on the third. Proposition 2.5, it says that addition of natural numbers is associative. So he's asking us to prove associativity. So here we go. I'm using his hint. Let B and C be fixed natural numbers. Then the base step 0 plus B plus C is B plus C, which is the same thing as 0 plus B plus C, because 0 plus anything is equal to that thing. That was one of the axioms. So that shows that the base step is satisfied. Going on to the inductive step, assume for some natural number A plus in parentheses B plus C is equal to A plus B in parentheses plus C. Consider the successor of A plus B plus C. That's equal to, in brackets, A plus, and then in parentheses, B plus C, the successor of that. And that's equal to, here I can associate by the inductive hypothesis. That's equal to the successor of, in brackets, A plus B in parentheses plus C. And then that's equal to the successor of A plus B plus C, which is equal to the successor of A plus B plus in parentheses. That, I'm just shifting the parentheses around here, but the successor of A plus B plus C is equal to the successor of A plus B in parentheses plus C. So that shows associativity holds. All right, by induction. All right, exercise 2.2.2, prove lemma 2.2.10. He gives another hint here. He says, use induction. The induction here is somewhat degenerate in that the inductive hypothesis is not actually used, but this does not prevent the argument from remaining valid. And then he just refers to the discussion on implication and causality in Appendix A2, which I haven't done on the YouTube channel, but like I said, I will be doing Appendix A on the Patreon page. Let me just, before I actually show you my proof here, let's go back to Lemma 2.2.10 just to refresh our memory on what that says. So here's the lecture note, the lecture summary, not the lecture summary, the section summary for section 2.2. Let me see if I can find the lemma. Here it is. Let A be a positive number. Then there exists exactly one natural number B such that the successor of B is equal to A. So this is the lemma that we're going to prove in the next exercise over here. All right, so let's do it. Again, unsurprisingly, it's by induction. So let A be a positive natural number. The successor of 1 is equal to 1. And if we assume that that's equal to the successor of n, that implies that n is 0 by axiom 2.4. So that shows that the inductive step is satisfied. I'm sorry, that shows that the base step is satisfied. And then going on to the inductive step in part 2, assume n is a natural number such that the successor of n is equal to a, then the successor of the successor of n is equal to the successor of a. And if we assume that that's equal to the successor of some integer m, that implies that the successor of n is the successor of m, which implies that n equals m by axiom 2.4, and that proves the lemma. All right. Exercise 2.2.3. I apologize for the sniffling too. I don't know why my nose is running in all these videos that I've been posting lately, but it just seems to happen before I turn the video on. Anyway, exercise 2.2.3, proof proposition 2.2.12. He gives another hint here. He says you'll need many of the preceding propositions, corollaries, and lemmas. This is the one that's long, and the only reason it's long is because there's a bunch of parts to it. Let me just show you the proposition that he's talking about, and then we'll go through the proof of each of the pieces. All right, so here's the proposition 2.2.12, basic properties of order for natural numbers. So I already talked about this in the summary for this section, but let's just remind ourselves of what it says. Let A, B, C be natural numbers, then all these parts are true. So part A, order is reflexive, which means that A is always greater than or equal to A. Part B, order is transitive, which means if A is greater than or equal to B, and B is greater than or equal to C, then A is greater than or equal to C. Part C, order is anti-symmetric, which means if A is greater than B and B is greater than, if A is greater than or equal to B and B is greater than or equal to A, then A is equal to B. Part D, addition preserves order. So which means if A is sorry, A is greater than or equal to B if and only if A plus C is greater than or equal to B plus C. Part E says A less than B if and only if the successor of A is less than or equal to B. And finally, part F, A less than B if and only if B equals A plus D for some positive number D. So let's go through the proof of each of these parts separately. All right, so let's prove part A first. So here, if you remember, part A is greater than or equal to A for all natural numbers A. So just using the definition of greater than or equal to A by definite by the one of the axioms. I forget which axiom it was, but A is equal to 0 plus A, which means that A is greater than or equal to A from the definition of greater than or equal to. Maybe I should just remind you of what that is because it might have been a little while since you saw the videos. This is the definition of the ordering of the natural numbers. Let n and m be natural numbers. We say that n is greater than or equal to m, and write n greater than or equal to m, or m less than or equal to n, if and only if n is equal to m plus a for some natural number a. That's what it means to be greater than or equal or less than or equal. So, okay. So that proves reflexivity. Part B, transitivity, A greater than B and B greater than, sorry, A greater than or equal to B and B greater than or equal to C implies that A is greater than or equal to C. So here's the proof. Let A, assume the hypothesis is true. Let A greater than or equal to B and B greater than or equal to C. Then A is equal to N plus B and B is equal to M plus C. Again, by the definition of the order relation on the natural numbers, then A is N plus B is equal to N plus M plus C. And by associativity, that's the same thing as N plus M plus C, which shows that A is greater than or equal to C. All right. Part C, A greater than or equal to B and B greater than or equal to A implies A equals B. So here's my proof. Let A greater than or equal to B and B greater than or equal to A, then A is B plus N and B is A plus M, which implies that A is A plus M plus N, which means that A is, which by associativity is A plus M in parentheses M plus N, which implies that M plus N is equal to 0, right? So that means M is 0 and N is 0 by corollary 2.2.9. Therefore, excuse me, therefore, A is equal to B plus 0 equals B. So A is equal to B. All right, part D, A greater than or equal to B if and only if A plus C greater than or equal to B plus C. So here's my proof. Let A greater than or equal to B, I'm assuming this hypothesis first, then A is B plus N by definition, then A plus C equals B plus N plus C, and again, by associativity, that's equal to B plus N plus C, equals B plus C plus N by commutativity, which is equal to, in parentheses, B plus C plus N by associativity, which implies that A plus C is greater than or equal to B plus C by the definition. And then to go in the reverse direction, now we assume that this is true and show that it implies this. So assume A plus C is greater than or equal to B plus C. That means that A plus C equals B plus C plus N equals B plus, in parentheses, C plus N by associativity, equals B plus N plus C by commutativity, which is equal to B plus N in parentheses plus C, again by associativity. Then A plus C is B plus N plus C, which implies that A is equal to B plus N by proposition 2.2.6. Therefore, A is greater than or equal to B. So that shows part D is true. All right, part E, A less than B if and only if the successor of A is less than or equal to B. All right, here's the proof. Let A less than B. Again, assuming this hypothesis first and showing that this follows, then B is greater than or equal to A and B is not A. That's part of the definition of the order. I didn't read that part out, but here the second part says, we say that N is strictly greater than M and write N greater than M or M less than N if and only if N greater than or equal to M and N is not equal to M. So I'm just using that definition here. Where was I? So let A less than B, then B is greater than or equal to A and B not A. Then B is equal to A plus N for some positive natural number N, since if N is 0, b equals a plus 0 implies that b is a, which would contradict the fact that b is not equal to a. Then the successor of b is equal to the successor of a plus n, which is equal to a plus the successor of n. If n is 1, then the successor of b is a plus the successor of 1. I'm using how do I say it? I guess maybe it's just easier if I show you. There's a remark that he has in the section that I prove here that he doesn't prove in the book. It's another case where he just says, why is this true? Let me just see if I can find it in the section just so I can show you what I'm using here. I think I just labeled it corollary instead of corollary with a number after it. Just bear with me. Here we go. So he says this in a remark, and he just asks, why is this true? So I proved it. He doesn't prove it in the book, but I'm using this because I already proved it. So here's the corollary. For any natural number n, the successor of n is n plus 1. So here's the proof. I actually proved this already, but I'll go through it again. Let n be a natural number, then n plus 1 is n plus the successor of 0 by definition of 1. The number 1 equals n plus the successor of n plus 0, which is equal to n the successor of n. So I'm using that fact here to write the successor of b equals a plus the successor of 1 if n is equal to 1. Right, that's equal to the successor of a plus 1, which is the successor of a, which implies that b is equal to the successor of a. That's from I forget what number axiom that was, but it's one of the axioms. If n is not 1, then the successor of b is b plus 1, which is equal to the successor of a plus n, which is equal to the successor of a plus m plus 1, which is equal to just using associativity, the successor of a plus m in parentheses plus 1. Therefore, b plus 1 is equal to, in parentheses, successor of a plus m, close parentheses, plus 1, which implies b is the successor of a plus m for a positive natural number m. That's by the cancellation property, which implies that b is greater than the successor of a. Therefore, b is greater than or equal to the successor of a. Right, and then now we assume the reverse and show, assume this and then show this. So let the successor of a less than or equal to b. So again, if you notice, that's this part here. I'm going to assume this, and I'm going to show that this is true. Then b is the successor of a plus n for some natural number n, just using the definition again. Then b is the successor of a plus n, which is equal to a plus the successor of n. Then the successor of n not 0 by axiom 2.3 implies b is greater than or equal to a, and b is not a, therefore a is less than b, and that proves that part. All right, part F says, if you recall, a less than b if and only if b is a plus d for some positive natural number d. All right, so let's start with this hypothesis and show that this is true. So let a less than b, then b is greater than or equal to a, and b is not equal to a. Then b is equal to a plus d for some natural number d, again, by definition. Furthermore, d is positive since b is not equal to a. Let b equal a plus d for some positive natural number d, then b is greater than or equal to a by definition. Furthermore, b is not equal to a since b equals a plus 0 equals a plus d, implies d is 0, which contradicts the fact that d is positive. Therefore, a is less than b, and that proves part F. And was that the last part? Yeah, so you can see that was really the longest one, but the only reason it was long was because there were so many parts to it. Each individual proof was not that long. All right, next one, exercise 2.2.4. Justify the three statements marked Y in the proof of proposition 2.2.13. Let me just show you that's the trichotomy law, but let me just show it to you again so your memory is refreshed. Let's see, I think it was towards the end. Here we go. This is the trichotomy law for the natural numbers. So let A and B be natural numbers, then exactly one of the following statements is true: A less than B, A equals B, or A is greater than B. So he does give a proof sketch of this in the book, but there's a few statements that he says why after, meaning that he wants you to prove those things. So instead of proving this statement in the chapter section itself, I said I'll prove this after I do the exercise where I prove those lemmas first. Then we can just use them and prove the theorem. So after I show you the proof of those statements, then I'll prove the trichotomy law. Okay, so here are the statements that he says, that he asks you to prove in the proof sketch for trichotomy. All right, so the first one he says is 0 less than or equal to B for all natural numbers B. So that just follows from definition. B is equal to 0 plus B, therefore it satisfies the definition of 0 being less than or equal to B. Right. The second statement is if A is greater than B, then the successor of A is greater than B. So here's the proof. Let A greater than B, then A is B plus N for some positive natural number N. Then the successor of A is the successor of B plus N, which is equal to B plus the successor of N. And the successor of N is not 0 by axiom 2.3, which implies that the successor of A is strictly greater than B. Right, and then the third statement is this one: if A is equal to B, then the successor of A is greater than B. Here's the proof. Let A equal B, then the successor of A equals the successor of B, which is equal to B plus 1. Again, I'm using that fact that I proved before. So, and that implies that the successor of A is greater than B, since 1 is a positive number. Okay, so now that we have those, we can prove the trichotomy relation for the trichotomy property of the natural numbers. So here's the proof. In both cases where A is greater than B or B is greater than A is not equal to B by definition. So assume then that A is greater than B and B is greater than A. Then that means A is B plus N and B is A plus M for some positive natural numbers N and M. Then A equals A plus M implies M is equal to 0, and B equals B plus N implies N is equal to 0. And that contradicts the fact that M and N are positive, right? So they can't be true all at the same time. To prove that one of these is true for all natural numbers, fix the natural number B, and then we do this by induction. So for the base step, 0 is less than or equal to B by star, which we just proven. So 0 is B or 0 is less than B. And then going on to the inductive step. Let A be a natural number such that A satisfies the trichotomy property. If A is greater than B, then the successor of A is greater than B by double star, that statement that we proved a second ago. If A is equal to B, then the successor of A is greater than B by triple star. If A is less than B, then the successor of A is less than or equal to B by proposition 2.2.12. Then that means that the successor of A is either less than B or the successor of A is equal to B. And that shows all the cases. So only one and only one of those things are true of the natural numbers. I'm sorry, of each natural number, or each pair of natural numbers. Okay. Here's exercise 2.2.5, prove proposition 2.2.14. He gives a hint for this one as well. Define Q of n to be the property that P of M is true for all M naught less than or equal to M less than N. Note that Q of n is vacuously true when N is less than or equal to M naught. This is the proposition 2.2.14 is the strong induction principle. Let me just read it out for you again, just so you have it in your mind while we're proving this. So here's the propositions. This is called the strong principle of induction. Let M not be a natural number and let P of M be a property pertaining to an arbitrary natural number M. Suppose that for each M greater than or equal to M naught, we have the following implication. If P of M prime is true for all natural numbers, M naught less than or equal to M prime less than M, then P of M is also true. In particular, this means P of M naught is true, since in this case the hypothesis is vacuous. Then we can conclude that P of M is true for all natural numbers M greater than or equal to M naught. right? And he says, proof left for the exercise, which we'll just do now. Okay, so I'm going to use his hint. Let Q of n be defined as in the hint, and we're going to do this by regular induction. So the base step, Q of m naught, is vacuously true since the set of all natural numbers m such that m naught less than or equal to m less than m naught is empty. So that shows that the base step is satisfied. Step two, the inductive hypothesis, inductive step. So we start with the inductive hypothesis. Let n be a natural number, n greater than m naught, such that Q of n is true. Then P of m is true for all m naught less than or equal to m less than n, implies P of n is true. Therefore, P of m is true for all m, such that m naught less than or equal to m less than the successor of n, which implies that Q of the successor of n is also true. Therefore, the inductive step is satisfied. Since Q of n is true for all natural numbers, P of n is true for all natural numbers n by the principle of mathematical induction, so axiom 2.5. Right, so that proves strong induction. We've done something similar to this, if you remember, back in Spivak, so hopefully this is not something new, but maybe you didn't see this Vivek video. I don't know. Anyway, next exercise set. Sorry, the next exercise question. This is 2.2.6. Let n be a natural number and let P of m be a property pertaining to the natural numbers, such that whenever the successor P of the successor of m is true, then P of m is true. Suppose that P of n is also true. Prove that P of m is true for all natural numbers m less than or equal to n. This is known as the principle, excuse me. This is known as the principle of backwards induction. And again, he gives a hint here, apply induction to the variable n. So that's what we'll do. And I use a similar sort of trick that he uses in the previous question. So let Q of n be the proposition that P of n is true, implies P of m is true for all 0 less than or equal to m less than equal to n. Right? Q of 0 is vacuously true. So that's the base step. The inductive step, then, let Q of n be true for some natural number n. Assume that the successor of n, sorry, this is getting me tongue-tied, always having to say the successor of. But anyway, P of the successor of n is true. Then P of n is true by the, that's a property of that property. That implies that Q of the successor of n is true. All right, so that just by, regular induction, this follows. All right, last question in the exercise set for 2.2. This is question 2.2.7. Let n be a natural number and let P of m be a property pertaining to the natural numbers such that whenever P of m is true, P of the successor of m is true. Show that if P of n is true, then P of m is true for all m greater than or equal to n. This principle is sometimes referred to as the principle of induction starting from the base case n. So in other words, you don't have to start at 0. You can start at some other natural number, and as long as the truth of the proposition sort of like propagates through all the natural numbers after n, then it's true for all natural numbers after n. All right, so here's the proof. Assume P of m naught is true and define Q of n to be the proposition that P of m naught plus n is true. And again, we're just going to do this by induction. Base case, P of m naught plus 0 equals P of m, sorry, I called it m naught, but P of m naught plus 0 equals P of m naught is true, implies that Q of 0 is true. So that's the base step. Step 2, assume Q of n is true for some natural number n, then P of m naught plus n is true, which implies that P of m naught plus the successor of n is true, which implies that Q of the successor of n is true. And that satisfies the induction. So, and I think that's it. That's the last question for this exercise set. Let me stop the screen share. Okay, so like I said, I'm going to, I'm almost done writing up my section summary for section 2.3. Once I finish that, I'll make the video on it. It's probably not going to be tonight. It might be tomorrow or the day after. And then there's one exercise set for chapter 2. And I think what I'm going to do after I finish chapter 2 is I'm going to actually go through Appendix A on the Patreon page. I'll leave a link to the Patreon page down below if you want to check that out. It does cost $5 a month, but you get a lot of extra content for that $5 a month. And you can quit anytime that you want. Then I'll go on, once I finish that, then I'll go on to chapter 3, excuse me, and 4 and 5. I want to at least in the near future, within the next, like, maybe month or so, finish up all the stuff in Tao's book from about the number system. So the natural numbers he does some stuff on set theory, which is chapter 3. We'll do that. And then he does integers and rationals, and then he does the real numbers by he does them in he constructs the real numbers with Cauchy sequences instead of Dedekind cuts. We will see the construction of the real numbers with Dedekind cuts when we get to it in Spivak, because Spivak does the derivation of the real numbers as well, or sorry, construction of the real numbers as well, but he does it with Dedekind cuts. So we'll be able to see both methods, which will be nice. But anyway, that's the end of this video. Let me know what you guys think in the comments below, and I'll see you in the next one. So keep learning, everybody.